So in this video, we're going to talk about how to determine possible solutions to a system of two or more inequalities. So remember, when we were talking about systems of inequalities, we said that any point that's in that overlapping region is going to be a solution to the system. So that overlapping region is also called a feasible region. So any point within the feasible region will be a solution to our system. So you can see in this example, the only point that's within the feasible region is 1, 2, because that's in the shaded region that overlaps in all three of these inequalities. So remember that a solution to a system of inequalities will be a point xy that makes all of the inequalities in the system true. So if we want to determine if 4, 3 is a solution to the system, we would go to all these inequalities and plug in 4, 3. So let's try doing that, because remember in 4, 3, that means that x equals 4 and y equals 3. So if we plug that into the first inequality, we get 3 is less than 2 times 4 minus 4. So that's saying that 3 is less than 8 minus 4, which says that 3 is less than 4, which is true. Okay, but remember, it has to make all three of the inequalities true. So now let's try the second one. So we have 3 is greater than or equal to negative 1/2 times 4 plus 3. So that tells us that 3 is greater than or equal to negative 1/2 times 4. That's going to be negative 2 plus 3. So we have 3 is greater than or equal to 1, which is also true. Okay, and now finally we need to make sure that it works in our third inequality. So that's x is greater than or equal to 0. So we plug in x, which is 4, and 4 is greater than or equal to 0. So that's also true. So that means that 4, 3 is a solution to this system, right? So we would say yes. Okay, so now let's re-examine the word problems from the last video a little more closely. So you'll notice that the video before this and then the video today and then the video that comes after this are going to be kind of like a series. So we're going to be studying different aspects of those three word problems that we started talking about. Okay, so remember the first problem was this: the sum of two numbers is no more than 10. The first number increased by twice the second number is more than 5. The difference of the first number and second number is at least 3, and this can be represented by the following system of inequalities. So remember, this is the system of inequalities that we wrote in the last video, and I just have them typed out here. So now we want to think about, is it possible for the first number to be 7 and the second number to be 1? Okay, so what does that mean in terms of this problem? Well, we know that the first number is x and the second number is y. Okay, so really all this is basically telling me is it possible for 7, 1 to be a solution to the system of inequalities? So there's actually two ways we can go about doing this. One way is we can go to Desmos and we can graph all three inequalities, right? We can say x plus y and then is less than or equal to 10. And then we have x plus 2y is greater than 5. And then we have x minus y is greater than or equal to 3. Okay, so you can see here, here's our feasible region, right? Because that's the region where all of the shading overlaps, like this triangle right here. And then now I'm going to ask Desmos to graph the point for us, 7, 1, so that we can see whether that point is in the feasible region. And you can see pretty quickly that it is. Okay, so it is possible for the first number to be 7 and the second number to be 1. Another way to check this is algebraically. You can do what we did in the previous example and plug these values in for x and y. So in the first inequality, that gives us 7 plus 1 is less than or equal to 10. So 8 is less than or equal to 10, so that's true. Okay, and then check the second inequality. We have 7 plus 2 times 1 is greater than 5. So we have 7 plus 2 is greater than 5. So that's saying that 9 is greater than 5, which is also true. And then finally, we have 7 minus 1 is greater than or equal to 3. So that's saying that 6 is greater than or equal to 3, which is also true. Okay, so that's another way of checking if it's possible for the first number to be 7 and the second number to be 1. So remember, we also had this second problem, which was talking about Barber's Bakery and their pecan order, right? So they were needing to process at least 35 pounds of pecans, and they have stores that can hold a maximum of 70 pounds of pecans. Since pecans from North Texas cost $27.50 per pound and pecans from San Saba cost $10.25 per pound, they can spend no more than $1,200. So from all that information, we were able to write these inequalities here. So notice that I've added in two more inequalities, okay? So I added in that x is greater than or equal to 0 and y is greater than or equal to 0. And so those are two inequalities that we add in when we're talking about real life situations, okay? Because if we think about it, if they're ordering pecans, they can't order negative pecans, right? See, in this previous problem, we were just talking about two numbers. Okay, so we didn't have to add any extra restrictions because those two numbers could have been positive, negative, fractions, decimals, like anything, right? But here we're talking about weights of pecans. So if you're ordering from a distributor, you can't really order negative pecans. Okay, so that's why we add in those two, x greater than or equal to 0 and y is greater than or equal to 0, because we want to make sure that our solutions are reasonable. So let's think about the first situation. It says if Barbara's Bakery orders 60 pounds of pecans from North Texas and 80 pounds from San Saba, would that satisfy the conditions stated above? Well, we can do this one of two ways, right? So we can go to Desmos and type in our inequalities. So let's go ahead and do that. So we have x plus y is greater than or equal to 35. And then we have x plus y is less than or equal to 70. And I want to make sure I'm keeping an eye out for my overlap as I'm, graphing these inequalities. Okay, so here we found the region of overlap in the middle. And now the third inequality, so 2750x plus 1025y, and that's less than or equal to 1200. And then, okay, so you can see now this is our region of overlap. And then let's add in our x is greater than or equal to 0. So kind of going to zoom in and on that region. It's going to be here now. And then we have y is greater than or equal to 0. Okay, so that gives us this very specific region of overlap here that's in the middle. Um, and so it's going to be like this shape right here, right? So it's going to be bounded by the x-axis and the y-axis. So it's going to be right there. Okay, so now we want to think about, is it possible for them to order 60 pounds and 80 pounds? So remember, North Texas was X and San Saba was Y. So A is asking us, well, is it possible to have 60, 80 in our system of inequalities, right? So let's go ahead and graph that point. 60, 80, and you can see that is way out of that region of overlap that we identified, right? So that is way out there. So it's not possible, right? So I'm going to go ahead and say no on that one. And then let's try B. Okay, so B is asking us, is it possible to have 30 from North Texas and 24 from San Saba? So that's going to be 30, 24, right? That's going to be the point that we're looking for. So we have 30, 24. And you can see that is within that region of overlap, right? It's right there. So we're saying yes on that one. But remember, you can always check this algebraically. So you can go ahead and plug into the inequalities and make sure that it makes our inequalities true. So when we try A, so we have 60 plus 80 is greater than or equal to 35. So 60 plus 80 is 140. 140 is greater than or equal to 35 is true. And now we want to try 60 plus 80 is less than or equal to 70, and you can already see that's not true, right? So that's why this system will not work for this solution. Okay, let's try B now. So if we plug in 30 and 24, 30 plus 24 is greater than or equal to 35 because 54 is greater than or equal to 35. Then if we try the second inequality, we have 30 plus 24 is less than or equal to 70. So that's telling me that 54 is less than or equal to 70. So that works. And then finally, we have 2750 times 30 plus 1025 times 24 is less than or equal to 1200. So I'm going to use my calculator to help me out on that one. So I have 2750 times 30 plus 1025 times 24. And that gives me 1071, and that is less than 1200. Okay, so that works there too. And remember that we also want to check that both these values are greater than or equal to 0. 30 is greater than or equal to 0, so that works, and 24 is greater than or equal to 0. So you can see it works in all of the inequalities. So that's why 3024 is a reasonable solution, but 6080 does not work. Okay, so now you can go ahead and pause the video and try doing this example on your own. All right, so here, remember, we have this problem where Ronald was organizing snacks for his movie night. And so we had these inequalities that we set up in the previous video. Since we're talking about a real life situation, I added in that x is greater than or equal to 0 and y is greater than or equal to 0 because it doesn't make sense to have a situation where he buys negative bags of chips or negative bags of pretzels. So in part A, it wants us to think about could he buy 36 bags of chips and 10 bags of pretzels? So here I have graphed the system of inequalities. And I'm just going to go backwards so that you can see this region of overlap. Well, so notice that, from my first two inequalities, this purple sliver right here kind of tells me the overlap region. And then I'm going to add in the third inequality. So you can see that's this region now here. When I add in x is greater than or equal to 0, that's going to restrict it to values to the right of the y-axis. And then I add y is greater than or equal to 0. So that's now restricting it to this section right here. That's in my graph. So if we are thinking about could you buy 36 and 10, so that's going to be the point 3610. And if we graph that on our grid, we can see that that is way beyond that feasible region. So it's not going to work for this system. If he's asking us if he could buy 20 bags of potato chips and 5 bags of pretzels, we can see that 25 is well within our feasible region. Remember, we can also check algebraically. So if we check 3610 algebraically, you can see that it doesn't work for the second inequality. But then if we check 25, you can see that it does work for all of the inequalities in our system. All right. So just, just some math humor. When I was working on this last problem with Ronald and his snacks, it just made me think of this meme I've been seeing everywhere. Because, there's always a joke about how math problems are about somebody buying like a shopping cart full of chips. And so I found this picture and it just made me think of this last problem. Um, all right, so the feasible region tells us all the possible solutions to a system of inequalities. Remember that an ordered pair XY represents the solution to a system of inequalities if it makes both inequalities in the system true.